Hello dear students, good morning to each and everyone. Good morning guys. Am I audible properly? First of all tell me, audio and video both are clear or not? Tell me guys. Am I audible properly? From today, we will start new series. Small signal analysis of BJT and MOSFET like never before. Okay, I will provide you complete concept, detailed concept of this topic. Small signal analysis of BJT as well as MOSFET. Okay, and all of you know very well this topic is very much important guys in analog electronics. Okay, and so many students suffer difficulty from this topic guys. Okay, so first of all tell me guys, am I audible properly? Audio and video both are clear or not? Tell me. Am I audible properly guys? First of all tell me. Okay. So small signal analysis of BJT and MOSFET. This is part 1 and daily I will conduct this lecture. Okay. This will be completely in English guys. Completely in English. Okay. So please सेशन को लाइक एंड शेयर करके बाकी लोगों को इन्फॉर्म कर दीजिए आप. चलिए प्लीज लाइक एंड शेयर दिस सेशन. Small signal analysis of BJT. Small signal analysis or it is also known as amplifier analysis. Amplifier analysis. It is also known as amplifier analysis or it is also known as AC analysis. AC analysis of BJT circuit or MOSFET circuit. AC analysis. Okay. So small signal analysis or small signal analysis or amplifier analysis or AC analysis. Yes, good morning to each and everyone. Now tell me, am I audible properly? Audio and video both are clear? So this is part 1 guys, and every day I will conduct this lecture in English only. In English only guys. Okay. So first of all tell me, am I audible properly? And please like this session and share with your friends also. Okay. So let us start guys. First I will teach you small signal analysis of BJT, then later we will study MOSFET also guys. Complete each and every configuration, common emitter, common base, common collector, without bypass capacitor, with bypass capacitor, as well as we will solve different questions also. Okay. So let us start guys. Let us start first we will understand the small signal analysis of BJT. Small signal, or it is also known as amplifier analysis or AC analysis. Small signal analysis of BJT. First we will see the small signal analysis of BJT. Okay. Small signal analysis of BJT, or it is also known as amplifier analysis, or we can say AC analysis. Okay. So first of all we need to understand the linear equivalent circuit of BJT under this small signal condition. Small signal means AC signal. Okay, applied AC signal. So AC signal, there is a low fluctuation in AC signal, that is known as the small signal, and which is AC, that's why it is known as AC analysis. And BJT operates in the active region and it acts as an amplifier, that's why it is known as amplifier analysis. So small signal analysis or AC analysis, or we can say amplifier analysis. Okay. So first of all we need to understand the linear equivalent circuit of BJT under the small signal condition. Okay. First of all you need to understand the linear equivalent circuit or linear equivalent model of BJT under the small signal condition, which is very much important guys. So I will teach you different models also guys, like T model or we can say RE model, then beta RE model, then pi model, then H model, and we will solve different questions based on each and every model. Okay, and I will provide you the simple and sober tricks to solve all the questions. Very much easy trick. Okay, so let us understand. See, this is BJT, guys. First of all, I am taking NP and BJT. Then we will see PNP BJT also. Okay. So see here, all of you. First of all, I am considering this NP and BJT. See, this is the symbol of NP and BJT. This is collector arrow, that means this is emitter, and this is base. NPN, why NPN? Because this current is leaving, guys, leaving from the emitter, we can say. Leaving from the emitter, that's why emitter terminal this is, and this is NPN. So this is N, P and N, guys. Okay, NPN transistor. We will see PNP also, guys. Okay, now see, we can see, guys, here there is a PN junction present between base and emitter. There is a PN junction present between base and emitter. You can see, guys, there is a PN junction present between base and emitter, and one more PN junction present between base and collector, or we can say there is a PN junction diode, internal PN junction diode present between base and emitter, as well as base and collector also, guys. Okay, so let us mark this. See, like this we can say there is a PN junction present between internal between base and emitter, okay, and one more PN junction present between base and collector, guys. Correct, like this. See here, let us mark this is DE, guys, PN junction diode DE. Okay, this is the internal PN junction. Okay, this is not externally connected diode, guys. Remember this thing. That's why I marked as a dotted line, guys, dashed line, not solid line, because these are the internal diode, we can say. Okay, internal diode. So here when there is a one PN junction present between base and emitter, one more PN junction present between base and collector. Okay, let us mark this diode as a DE. Okay, and let us mark this diode as a DC, guys. Correct. Now small signal analysis, or we can say amplifier analysis, guys. Now please concentrate here. Small signal analysis or small signal amplifier analysis. So see here, see, for the amplifier analysis, or to act as this BJT as an amplifier, to use this BJT as an amplifier, it should operate in the active region, guys. It should operate in the what? Active region. Remember this thing. This is what? Amplifier analysis. And for the BJT to act as an amplifier, it should operate in the active region. Remember this thing. It should operate in the what? Active region. It should operate in the active region. It should operate in the active region. Correct? This BJT should operate in the active region. Active region. Okay, to act as an amplifier, or to use BJT as an amplifier, it should operate in the active region only, guys. Correct? It should operate in the active region only. Okay, so we are considering here active region. Correct? And for the active region, for the BJT to BJT operate in the active region, this diode should be operate in the forward bias, this diode should operate in the forward bias, and this is in reverse bias, guys. Correct? Remember this thing. This is in forward bias and this is in reverse bias. Are you getting? This should operate in what? Reverse bias. And if this diode operates in the forward bias, then we can say the BJT operates in the active region. So this is the basic fundamental that you have to understand. Correct? In order to operate BJT in active region for an amplifier, this PN junction should operate in the forward bias and this PN junction should operate in the reverse bias. Now see, diode operates in reverse bias means what? Simply it acts as an open circuit, guys. Simply it acts as an open circuit. Correct? Simply it acts as an open circuit, guys. Okay, it acts as an open circuit. Correct? So we can say equivalent circuit here. What should be the equivalent circuit? So here we can draw like this. This is base, again this is collector, and this is the emitter. Now see, this PN junction operates in the forward bias and this in reverse bias. It acts as an open circuit between base and collector. This PN junction open circuit, and there is PN junction present between base and emitter. Okay, so there is PN junction present between base and emitter. This is DE, operates in what? Forward bias. This operates in the forward bias. Correct? This operates in what? Forward bias. Correct? And this reverse bias, that means open circuit, guys. Reverse bias, that means open circuit. Now let us mark current, guys. Here say this is the collector current. Okay, this is collector current, which is nothing but dependent collector current, which is known as what? Beta IB also, guys. IC equal to beta IB. Correct? IC equal to beta IB. This is emitter current here, emitter terminal. That's why this is the emitter current. Okay, and this should be base current, guys. This is the base current. Okay, now we can draw this BJT in very simple manner. Okay, so you can observe, guys, there is a PN junction between base and emitter. Correct? There is a PN junction diode present between base and emitter. Correct? There is a PN junction diode present between base and emitter, and from collector dependent current is coming, guys. Correct? Dependent current is coming. So equivalent circuit we can draw like this. See, here this is junction, one junction, guys. Okay, this is junction, this is base terminal. So between base and emitter, one PN junction. You can see, guys. See, between base and emitter, there is one PN junction. See here, there is one PN junction between base and emitter. Can we say like this? Between base and emitter, there is one PN junction. See, you can see, guys, here between base and emitter there is one PN junction. Let us consider this is base terminal, this is base terminal, this is emitter, guys. Correct? So between base and emitter, there is a PN junction. Okay, this is base current IB. Okay, this is your emitter current. Correct? This is your emitter current IE. Okay, this is also emitter current IE, guys. Yes or no? So from this diode, guys, emitter current is flowing. Yes or no? Can we say like this? Can we say like this? Tell me, are you getting? Can we say like this? See here, there is a PN junction present between base and emitter through which emitter current is flowing. Okay, so from this PN junction emitter current is flowing, guys. Okay, and upside there is a dependent current source. Okay, dependent current source, dependent current, guys. Collector current is dependent, IC equal to beta IB. IC is equal to beta IB. So we can say this is the dependent current source, guys. Okay, we can say this is the dependent current source. Are you getting? This is the dependent current source. Dependent current source, which is nothing but beta IB, guys. See, this is nothing but beta IB. IC is equal to beta IB. Correct? IC equal to beta IB. So you can see here, this is the base current, this is the collector current, which is equal to what? Emitter current. This is IC. Okay. So what is the emitter current? Can we say like this? IB plus IC, guys. Yes or no? IB plus IC. Can we say like this? See here. This is the base current, this is the collector current, and here this is junction. Okay, so apply KCL here. So entering current equal to leaving current. The emitter current equal to what? IB plus IC. So in active region, you can replace this BJT. You can replace BJT with this equivalent circuit. Yes or no? Because this PN junction forward bias. So here PN junction present. Okay, and this is operating in the reverse bias in the active region. Correct? So reverse bias. Okay, are you getting? Are you getting, guys, what I am saying? Correct? Fine. So this is the equivalent circuit of BJT in the active region, we can say. In the active region, this is the equivalent circuit of BJT. Okay. Now we will see the equivalent circuit for the DC point of view and for the AC point of view. Are you getting? Now we will see the equivalent circuit for the DC and for the AC, guys. DC equivalent circuit for DC and AC, guys. Okay. So let us see here. So this is base, this is collector, emitter. Here again I am writing PN junction. Okay, this is DE diode, guys. Okay, and here dependent current beta IB. So the equivalent circuit just we have seen. This is the equivalent circuit, guys. Equivalent circuit, collector, base and emitter. Collector, base and emitter. Okay, so this is the dependent current source. Here PN junction. Here this is PN junction diode. Okay, DE, through which emitter current is flowing, IE. This is base current, IB. this is junction, okay, and this is the dependent current source beta IB, correct. IC equal to what? Beta IB. This is beta IB. Now we will see the equivalent circuit for the DC analysis and equivalent circuit for the AC analysis, correct, because in the amplifier circuit DC for the biasing purpose present and AC for amplification, okay. So we can use the superposition theorem, that means you can use the DC analysis and AC analysis separately, okay. So now we will see the equivalent circuit for DC and for the AC, guys. So first is DC analysis, correct. DC analysis first, DC equivalent circuit of BJT, or we can say DC analysis, guys. DC equivalent circuit of BJT, or we can say DC analysis. So in DC, this diode act as a what? For DC, this diode act as a battery of V gamma, and here let us consider this is made up of silicon. So that's why we can consider this act as a battery of 0.7 for the DC, and for AC it act as a dynamic resistance, correct. For DC, this diode act as a battery of V gamma 0.7 if it is made up of silicon, and under the small signal condition, or for the AC, this diode act as a dynamic resistance. Simply you have to remember this thing, okay. So the equivalent circuit will be like this for DC. Okay, see, this is the equivalent circuit for DC analysis. If you are doing the DC analysis or Q point analysis or operating point analysis, then this will be the equivalent circuit. This is the beta IB current, IC equal to, this is we can say plus minus 0.7 volt, which is nothing but what? Between base and emitter, VBE, guys. VB is equal to 0.7 volt, okay. This is base, this is collector, and this is the emitter, okay. This is your base current and this is your emitter current. Can we say like this? Simply you have to replace this diode with battery of 0.7 volt. By default we are considering it is made up of silicon, that's why I am writing here 0.7 volt, guys, okay. So while doing DC analysis, all the AC sources are 0. AC sources should be 0. All the capacitor act as a open circuit for DC point of view, okay. So you are doing DC analysis, then you have to replace all the capacitor with open circuit, and all the AC sources are connected to ground. AC voltage sources are connected to ground, guys, okay. And you have to find all the DC parameters like collector current, like emitter current, base current, collector voltage, emitter voltage, then base voltage, VCE, Q point, okay. So you have to find this IEDC, guys, okay. Find IEDC here. Why IEDC? You have to find IEDC and ICDC. DC current, guys. Collect and emitter DC current, okay. Most important part, okay. Collector current and emitter current, DC collector current and DC emitter current you have to find while doing the DC analysis. And second part is the AC analysis or small signal analysis or AC equivalent model, guys, we can say. AC analysis or small signal analysis. Okay, AC analysis or small signal analysis, guys, है ना, correct. So see here, while doing AC analysis, simply you have to replace diode with what? Dynamic resistance. You have to replace this diode with what? Dynamic resistance, guys. You have to replace diode with dynamic resistance. Simply you have to replace diode with dynamic resistance. you have to replace diode with the dynamic resistance, and I'm marking it is RE because I'm marking it as RE guys, small RE, because it is at emitter through which emitter current is flowing, that's why. Okay, so again this is the dependent current source, and here as of now I'm ignoring the early effect guys. Later we will consider early effect also. So again this is base, this is collector, and see this is the emitter terminal, and this is your dynamic resistance guys, small RE. E stands for the emitter guys, small RE guys. Okay, now current, let us mark current. So here AC current, that's why small IB. This is beta into IB, which is nothing but your IC current, collector current. Okay, and this is your emitter current guys, emitter current, which is nothing but, if you apply KCL, then you will get beta plus 1 into small RE, correct? Beta plus 1 into small RE. Are you getting? Correct? So simply while doing AC analysis, you have to replace that with the dynamic resistance small RE. All are the AC components and all the currents are AC currents. And while doing DC analysis, you have to replace that with simple battery of 0.7. And in DC analysis, you have to find the Q point, all the DC currents, all the DC voltages, correct? And in AC analysis, or we can say amplifier analysis, so we will find voltage gain, current gain, input impedance and output impedance. 4 parameters we will find. Now what about this small RE guys? Small RE. So dynamic resistance, RD equal to what? Diode dynamic resistance, RD is equal to, formula is what? Eta Vt upon IDDC, where what is IDDC? DC current flowing through diode guys. What is IDDC? Formula is what? Eta Vt upon IDDC. So what is IDDC? DC current flowing through diode, and eta is what? Ideality factor. For multi-diode you have to consider eta equal to 1, and Vt thermal voltage at room temperature it is 26 millivolt. So here this is small RE guys. So small RE is equal to what? Dynamic resistance offered by this diode, DE guys. Now eta, we will consider eta 1 guys. Why eta 1? Because this is what? Multi-diode circuit. Here one diode and here one diode guys. You can see here one PN junction diode. See, there is a PN junction diode between base and emitter, there is a PN junction diode between base and collector. So we can say this is the multi-diode circuit. That's why we will consider eta equal to 1. So RE will be eta equal to 1. So Vt upon, what about the DC current flowing through this diode? What is the DC current flowing through diode? That is nothing but IEDC guys. See, DC current flowing through diode is what? Emitter current. Okay, so that's why in formula Vt upon IEDC guys, Vt upon IEDC. Okay, so this is the small signal equivalent model of BJT, or we can say this is the linear equivalent circuit of BJT under this small signal condition, or for the amplifier analysis, or amplifier equivalent circuit, or AC equivalent circuit, or small signal equivalent circuit of BJT. Okay, where beta is what? Current gain, IC upon IB, that you know very well. Is this clear? Tell me guys, is this clear? So this is what? Equivalent circuit, and this model is known as what? RE model guys, or T model. We can say this equivalent circuit is known as what? RE model or T model. This is the what? Small signal equivalent circuit of BJT guys. Small signal equivalent circuit, or AC equivalent circuit, or amplifier equivalent circuit of BJT. Correct? Is this clear? Tell me. Is this clear? Bhaumik and Vinu Harni, tell me. Is this clear till here? Till here clear guys? Tell me each and everyone. Fine? Okay. So this is the small signal equivalent circuit. We are ignoring the early effect. Okay, later we will consider early effect also. If we consider early effect, then there will be output resistance between collector and emitter also. And if we ignore the early effect, then the output resistance will be infinite. Okay. So later we will see the more equivalent circuit. This is the T model or RE model. Later we will derive the beta RE model. Then we will see the pi model also, then H model also, and then we will solve some important questions. Okay, so I will provide you technique to find the amplifier gain without drawing equivalent model, guys. That is the important part. Without drawing any equivalent model, directly from the circuit you can get the correct answer of voltage gain or input impedance, output impedance. Okay, but that we will consider in next part. So this is part 1. Till now here you can note down this thing, guys. Okay, till now here you can note down this thing. Later we will see in subsequent module. Okay, so all of you, thank you so much watching me live on Gate Academy Global channel, and next part we will continue into subsequent module. Thank you, guys. Thank you so much.